product. So this graph is very useful. It explains to you what I just talked about. In here we have reactant. Usually in this case the reactant has more energy than the product. That's why the reactant is higher than the product in this figure. And then you have the, let me ask you this question. Is this reaction hexagonic or entagonic reaction? I'll give you 5 seconds to think about this. 5, 4, 3, 2, 1, 0. Time's up. This reaction is an hexagonic reaction because the reactant is higher than the product, so it is releasing, so reactant has extra energy. In order to convert into product, it has to release the extra energy. So since it goes down, become less energy, then the energy that is lost during the conversion of reactant to product will go as heat. So this is an hexagonic reaction. And then we have the two activation energy. The blue one, you can see that it has a higher activation energy, but the I would say the orange one, it has a less activation energy. What causes the difference? The difference is in the key. The orange one has enzyme. The blue one does not have enzyme. So in other words, the function of the enzyme is to lower the activation energy of the reaction. When we lower the activation energy, it will be easier to convert the reactant into product. So exactly how they function, enzyme will bind with substrate. Okay, what is substrate? Substrate is basically the reactant. We talk about reactant all the time, and then it suddenly changed to substrate, so it may confuse some of you. Substrate is basically reactant to form a complex. The complex here we call enzyme substrate complex. Enzyme substrate complex. After it forms the enzyme substrate complex, it will enzyme will detach, will release the product. So the substrate will become product now. At the beginning, you have enzyme and substrate, they are separate. So substrate is trying to bind to enzyme. After substrate binds to enzyme, they form enzyme substrate complex. Yes, and then enzyme will speed up the conversion of the substrate into product. And then after the formation of product, the product will be released to the from the enzyme. Okay, let's take a look at this picture here. It gives you a better idea. On the left hand side, we have the degradation. Degradation is basically hydrolysis. You may assume this is a hydrolysis. An example of degradation is hydrolysis. An example, okay? One of the many example hydrolysis. So what happened in here is that our substrate is like a polymer, and it binds to the active site of the enzyme of an enzyme, and then you will form something called enzyme substrate complex. And during this stage, the enzyme will speed up the breaking down of this polymer, and then you become product. Product will be the monomers. Enzyme will release the product after it is formed. You may assume the substrate is maybe sucrose. Let's say substrate sucrose. After binding into sucrase, sucrase is an enzyme that will break down sucrose into what? Do you remember? Sucrose is a disaccharide, and then after binding to sucrase, which is an enzyme that breaks down sucrose, what will be the monomers that made up of sucrose? I'll give you 5 seconds to think about this. 5, 4, 3, 2, 1. Time's up. Yes, the product or the monomer that form sucrose will be glucose and fructose. Now synthesis. Synthesis is basically degradation. Not degradation, sorry. Dehydration. I'm sorry. Dehydration. Dehydration synthesis. It is one of the example, dehydration synthesis. So you have two monomers, for example, again, glucose and fructose, that binds to an enzyme, and it has the active site. The enzyme will form enzyme substrate complex, and then after that, then the enzyme will release, and then the product will be the sucrose. So there are two models for explaining how enzyme works. One is called Induced Fit Model. What happened is that substrate and the active site, the shape is not perfectly matched, but it is close enough so that when the substrate goes into the binding site or the active site of the enzyme, the substrate forces itself into the active site and causes the slight change in shape. We call it conformational change. The conformational change in the shape of the active site will accommodate the substrate for binding it. We call it induced fit. And then there's another model called lock and key hypothesis, meaning that the substrate and the active site, they match perfectly. So it's like a lock, it's like a key going into a lock. So active site and then substrate. As you can see that the active site originally is like a this shape, and then after binding to a substrate, it becomes this shape. You can see that it is the induced fit model. The substrate does not. The substrate looks like a diamond shape or walnut shape, and then the active site originally is like a parallelogram. It's like a parallelogram. Yeah. So the substrate forces itself into active site so that the active site will change the shape. As the shape of the active site change, it will also change the protein structure as well. Enzyme substrate lock and key hypothesis. So it's a perfect fit. So the substance, the substrate and the enzyme, they are perfect fit. The enzyme is like a lock, the substrate is like a key. So that when the key is inside the lock, we call this enzyme substrate complex. Last but not least, name the enzyme that has an ASE for specific substrate. To break down lipid, we have lipase. To convert urea, you have urease. To break down maltose, you have maltase. To break down ribonucleic acid, we have ribonuclease. For break down lactose, we have lactase. So remember, when we see a word that ends with ASE, this is usually an enzyme, and they are most of the enzyme, they are protein. So that's the end of today's lecture.